Welcome, ladies and gentlemen. Today we are going to study matrices and explore its uses in our daily lives. Before we start studying matrices, I want to start with a question. What is a search engine on the internet? A search engine is a web-based tool that enables users to locate information on the World Wide Web. Here are some widely known search engines. Before learning matrices, we have to first learn what is a vector. Denote first the set of all real numbers by R. A vector of length n is simply a list of n elements called vector entries. The notation of a vector v having entries x1, x2 till xn is the following. The entries of a vector can in principle be anything: words, colors, numbers, shapes, and even signs. Unlike the last example, we will only look at vectors whose entries are real numbers. As in this case of real numbers, real vectors can be added or multiplied by a real number in a straightforward way. So let's take a look at how we add two vectors. It's actually pretty simple. We add the first entry of the first vector with the first entry of the second vector, and second entry of the first vector with the second entry of the second vector. And it goes on like this till the nth entry. Right now, we will only look at scalar multiplication of vectors. Suppose we multiply the vector with the number a. The product is a vector and each entry is a times the entries of the first vector. So let's solve some problems. Consider the following. In this problem, we are going to apply what we have learned in the previous section and add the entries of vector together. The resulting vector's entries are the addition of the two vectors' entries. Similarly, in this example, we are going to multiply pi with all of the entries of the vector to find the product. Now, we are ready to learn matrices. In a similar way to vectors, we define the notion of a matrix. A m times n matrix is a rectangular array of entries having height m and width n. This can also be seen as stacking n vectors of length m, one next to the other. Again, take the entries to be real numbers. This means that on row I and column 3, we find the real number ai3. For example, on the first row, second column, lies element A12. Now that we know the concept of matrices, we can learn about the multiplication of matrices. Let's look at the multiplication of two matrices. In order to find any element in the product, in this case let's suppose Cij, the following formula must be used. This formula basically states that in order to find Cij, we must multiply all the corresponding elements of the row I and column j and add. For example, the first element of row I is ai1 and first element of column j is b1j. We multiply both of them and add to the multiplication of the second element of row I and second element of column j. It goes on like this until the last element. Let's do some exercises with matrices. Let's multiply matrix E with matrix D. Matrix E's dimension is 3 by 2, whereas matrix D's dimension is 2 by 2. Since their dimension is not the same, we cannot multiply these two matrices. In this case, we have to first calculate the multiplication of a real number 3 and the vector. After calculating that, we have to add the product with the second vector, and we have the result. In this problem, we have to apply the formula we recently learned. In the first matrix, the first element of the first row is 2, and in the second matrix, first element of the first column is -1. We multiply both of them and add to the multiplication of the second element of the first row in the first matrix and the second element of the first column in the second matrix. The rest goes on like this until the last element. Do you remember the question I asked at the very beginning? Now that we have mastered the concept of matrices, we will learn its relation with the mathematics of Google search. We live in a computer era. Internet is part of our everyday lives and information is only a click away. Just open your favorite search engine like Google, Bing, Yahoo, Yandex and type in the keywords and the search engine will display the pages relevant for your search. But how does a search engine really work? At first glance, it seems reasonable to imagine that what a search engine does is to keep an index of all web pages, and when a user types in a query search, the engine browses through its index and counts the occurrences of the keywords in each web file. The winners are the pages with the highest number of occurrences of the keywords. These get displayed back to the user. However, this approach used in 1990s proved to be inefficient and problematic. Suppose we wanted to find some information about Coach Holding. We type in the word Coach and expect that Coach.com will be the most relevant site to our query. However, there may be millions of pages on the web using the word Coach, and Coach.com may not be the one that uses it most often. Suppose we decided to write a website that contains the word Coach a billion times and nothing else. Would it then make sense for our website to be the first one displayed by a search engine? The answer is obviously no. Modern search engines employ methods of ranking the results to provide the best results first that are more elaborate than just plain text ranking. One of the most known and influential algorithms for computing the relevance of web pages is the PageRank algorithm, used by the Google search engine. It was invented by Larry Page and Sergey Brin while they were graduate students at Stanford, and it became a Google trademark in 1990. The idea that PageRank brought up was that the importance of any web page can be judged by looking at the pages that link to it. Let's suppose the internet was made up of only 4 websites: page1.com, page2.com, page3.com, and page4.com. We can easily translate this graph into a directed graph with 4 nodes, one for each website. In our model, each page should transfer evenly its importance to the pages that it linked to. Node 1 has 3 outgoing edges, so it will pass on 1/3 of its importance to each of other 3 nodes. Node 3 has only 1 outgoing edge, so it will pass on all of its importance to node 1. In general, if a node has k outgoing edges, it will pass on 1/k of its importance to each of the nodes that it links to. Let us better visualize the process by assigning weights to each edge. Let's denote by A the transition matrix of the graph. Suppose that initially the importance is uniformly distributed among the 4 nodes, each getting 1/4. Denote by V the initial rank vector, having all entries equal to 1/4. Each incoming link increases the importance of a web page. So at step 1, we update the rank of each page by adding to the current value the importance of the incoming links. This is the same as multiplying the matrix A with V. At step 1, the new importance vector is V1 equals AV. We can iterate the process. Thus, at step 2, the updated importance vector is A squared times V equals A times AV. We notice that the sequences of iterates V, AV until a to the power of kV tends to the equilibrium value a to the power of 8v. We call this the PageRank vector of our web graph, and when listing the website with the highest PageRank vector will be at the very top. We have come to the end of our study. Here is the overview of the topics covered. I had an amazing time making this video, and here is the reflection part of our study. And here is my inner reflection while preparing this video. Special thanks to the Cornell University for providing us with lectures on PageRank algorithm and matrices. Thank you for watching my video, and goodbye.